Hello, today we will be solving this problem called towers. So we are given n cubes in a certain order and our task is to build towers using them. Whenever two cubes are on top of each other, the upper cube must be smaller than the lower cube. So we must process the cubes in the given order, and we can always either place the cube on top of an existing tower or begin a new tower. And our goal is to find the minimum possible number of towers. So the first input line contains an integer n that can be up to 2 times 10 to the 5th. Then follow n integers representing the size of the cubes, and they can be as large as 1 billion. And this is an example here. So we have 5 cubes and the minimum number of towers in this case would be 2. So let's find out why. So in this first example, we will try to come up with a solution. Here, the first cube, we have no choice. We cannot put it on top of another previous cube, so we have to start a new tower with this cube. So there is this new tower with size 3. Then we have this cube of size 8. So what are our possibilities? Either we put it on top of this cube or we start a new tower. Since 8 is larger than 3, we cannot put it on top of this. So we gotta start a new tower with base equal to 8. Okay, so we took care of that. Now we are at this position. So what are our choices for 2? Either we put it on top of this, or we put it on top of this, or we start a new tower. Since we are trying to minimize the number of towers we have, it would be a bad idea to put it as a new tower here. So what the choices we are left with is either to put it on top of this one or on top of this one. And if we choose to put 2 here, like if we put 2 here and then a 7 comes afterwards, this 7 cannot be placed on top of this 3. So we gotta start a new tower for this 3. And then we gotta for this 7, and then we will end up with 3 towers, which is not optimal because we could have placed this 2 here and placed the 7 here. So the idea here is if we wanna place a cube on top of an already existing tower, we better place it on top of the tower that can accommodate it and has the smallest possible size. So there is no point in putting 2 here since we can put it on top of this smaller tower. That's why we would put it here. Okay, and then comes 1. Same logic here. There is no point on putting it here because we're gonna restrain this tower, because we could just put 1 here and it would be better. So we put 1 here, and then our last element is 5. So we would just put 5 here. And we will end up with 2 towers. So if we summarize what we came up with, so we have some criteria we have to obey. Let's choose some other color. So first of all, if we have 0 towers, then we create tower. Here we have no choice as we had with this first element. Create tower. Okay. Then if we have existing towers, we would choose tower with smaller size. Choose tower with smallest size let's call this size x, such that x is strictly larger than our current size. And if no such tower exists, then we will just create new tower. That is to say, like here for 8, the towers we had were just 3. So we would choose a tower with smallest size x, such that x is larger than 8. But no such tower exists, so that's why we created another tower for 8. Okay, so this seems pretty straightforward, but how are we gonna go about this? Like here, would we just maintain our towers in a vector or something? Like if we go back at the beginning, we just had 3, then we added 8, then for 2 we would go through all these values and check for the one that is the smallest one that is greater than 2. So it would be this one, and our vector would become something like 2, 8, and then we would go to this one, and then our vector would become something like 1, 8, and for the final one it would become something like 1, 5. But what if we had something like, we had let's say we had 6 elements, and there were 1, 2, 3, 4, 5, 6. Then we would insert 1 first, so we would have a tower with size 1. Then 2 cannot be accommodated by 1, so we would have 1, 2. And then for this 3, we would have to check 1 and 2. And since none of them is larger than 3, we would just insert another 3 as another tower, and so on until we end up with 1, 2, 3, 4, 5, 6. And if you notice here, for each new element we have to compare it with all previous elements. And this is not practical, because for each element I, it would have to perform I-1 comparisons. So this would result in 0 plus 1 plus 2 and so on plus n-1. Sorry. So this would be equal to n times n-1 over 2, which is asymptotic to n squared in complexity. And this would TLE because n is up to 10 times to the 5th. So this solution is not practical. So we gotta think about something else. But before we do that, let's proceed to the second example. Let's try to solve this example. So as we said here, 3 is our first element, so our only choice is to insert it. Then 4 is our second element, it's larger than 3, so we'd insert it as well. Then for 2, it has 2 choices, and you would pick the smallest one closest to it, so it would be 3. We'd put a 2 here, then comes 1, so we'd put it here, and then comes 5. So since it's larger than all previous elements, we will put it here. Then comes 3, we'd put it here, then 4 here, then 3 again, we would put it here. And for this 2, it has 2 choices, and both of them are equivalent, so we'll just put it here, and the answer would be 3. And to go back to our dilemma, in order to perform what we want to do efficiently, there is a data structure that we're gonna introduce, which is multisets. So what is a multiset? So if we check out the CPP documentation, a multiset is a container that stores elements following a specific order. So it is sorted, and where multiple elements can have equivalent values. Like in this case, we saw that we had multiple values of 2s and 3s and so on, so we could not just use a set by itself. So that's why we need a multiset. So what can a multiset do? So we could insert elements into our multiset. So here it is. So we could insert elements into our multisets, erase elements, and here it is worth mentioning that if, for example, if we had a multiset that contains many occurrences of 2 and we performed an erase 2, it would erase all elements that were equal to 2. So that's why if we wanted to erase only one element, we would have to perform a find first. So we perform a find and it gives us an iterator to only one element, and then we erase that iterator instead of erasing all the values. Okay, and what is of interest to us here is this upper bound operation. If we check it out, so the upper bound operation returns an iterator pointing to the first element in the container, which is considered to go after val, which means that it is strictly greater than the element we passed into it. And that's exactly what we want in this problem. And if such elements cannot be found, then iterator to the end of the container is returned. For example, here we inserted 10, 20, 30 and so on, and we performed a lower bound and an upper bound. Since 30 exists in our multiset, so the lower bound of 30 would be itself. And in our case, if these were the towers, we wouldn't want to perform a lower bound because it would return 30, and we cannot place a cube of size 30 on top of a tower of size 30 because it has to be strictly larger. That's why we need upper bound. And the upper bound would return, for 40 for example, would return 50, and that's exactly what we need in our problem. Here it's worth mentioning that we might need erase too, because once we found, for example, here we had, if this was our multiset, in the beginning we just insert 3 into it, and then when we move to 4, we would perform an upper bound with 4, and it would return the end of our multiset, which means that no element in our multiset is strictly larger than 4. That's why we would add 4 to our multiset. Then move into 2, the upper bound would return 3. That's why we will need to erase this 3 because it's not the top of a tower anymore, and insert 2 instead. When we come to 2, we would perform the upper bound, which would give us 2. Then we would erase 2 and insert 1 instead, and so on. 5 would return the end of the multiset again. That's why we need to insert it. And then moving on to 3, the upper bound of 3 would return 4. That's why we put 3 on top of 4, and we will erase 4, insert 3, 4 again, then we would erase 5, insert 4, 3, the upper bound would be 4, so we erase 4, and erase and insert 3. And see here we have 2 occurrences of 3. That's why multiset is a must in this context. Here again, finally we had these 2, so the upper bound would return either of these 3s, so we just take this one and put 2 instead. And if you notice, these are the top elements we ended up with, and the size of our multiset is equal to our answer. And as you can see here, upper bound is logarithmic inside in terms of complexity. So for each element here, for each element we have n elements, and for each element we perform an upper bound which is log n in complexity, and we perform either an insert or an insert plus erase. And if we check out the insert here, in complexity, it's also, if a single element is inserted, logarithmic in size in general, but amortized constant if a hint is given about the position given in is the optimal. So it can be, in worst case, it is logarithmic in size. So if n elements are inserted, n log n of size plus n, but linear in size if elements are already sorted according to the same ordering criterion used by the container. So what we have to retain from this is that it is log n in worst case. Okay, and what about erase? Complexity. For the first version, erase position amortized constant, so erase val logarithmic in container size. So all these operations are logarithmic. That's why our final complexity would be n times 3 times log n, because at most we're gonna perform 3 operations for each element, which is equal to O of n times log n. And this is about n times 6 or something like that, because log of 10 to the 5th, so ln of 2 or log 2 of 2 times 10 to the 5th would be equal, with logs we can bring this power outside, so it would be 5 times log 2 of 20, or actually of 10. Let's say we just have 10 to the 5th of 10, and log 2 of 10 would be 3, because 2 to the 3rd is 8 is closer to 10, so this would be something like 15 instead. So let's say 15. So our final complexity would be something like 15 times n, which is about 10 to the 6th, which is fine within these time constraints. So this wouldn't yelling. So that's pretty much it. Let's check out the code. So this is our problem. As usual, we're gonna start by reading the input. Then we're gonna declare our vector of cubes. We're gonna scan these values. Then we're gonna declare our multisets, and we're gonna call it towers. Then we're gonna process all our elements from 1 to n. So our first condition that we talked about is that if the multiset is empty, so if towers.size is equal to 0, we have no choice but starting a new tower. That's why we insert cubes into our tower, like creating a new element. Otherwise, as we said, we're gonna perform an upper bound with our value. So to perform an upper bound, we just apply this method to our multiset, and we pass the value into it. So we pass the value of cubes into our method, and it returns an iterator that points to that exact position. And if our iterator is equal to towers.end, that means it is outside, there is no value in our multiset that is strictly larger than cubes I, then our only choice is to insert cubes I. Otherwise, we're gonna insert cubes I because it became our the top element of some tower, and we have to erase the previous element of that tower. It's as we said here, like when we inserted one here, we had to erase these two first, and then we inserted the one. And at the end, the answer would be just the size of our multiset. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.